All right, let us start. We'll start by discussing that how much time one is needed to do a particular computation, and then that will lead us to the need for a parallel computer, okay, or parallel computations. Parallel computations, if you just read it from its uh, English language viewpoint, is just doing several computations together. So why do we need to do several computations together? So let's ask that question. To do that, let me define what is usually we will hear this very much. So it's called one flop. What is one flop? So flop is nothing but the short form of floating point operation. So one flop means that there is one floating point operations in happening in 1 second, so per second. So if my computer can do one floating point operation per second, so that I will say one flop. So what is a floating point operation? You can think of just adding two floating point numbers. Okay. Now this will definitely depends on how your floating point is defined. So this will depend on the implementation of the of float. So if it is a float 32 or float 64 or float 128, so you know that float 32 has 23 bit mantissa, 64 has something other with larger number of bits. So that those things, so which one you are using, so that will uh, decide that how much time your computer will take to do one floating point operation. But nevertheless, if I consider a very simple case where, so like you know that we have several cores in our machine. So you say that it's a 4-core processor or 2-core processor, dual core processor. So if I ask that if my computer, what is the flop of my computer? So how many floating point operations it can do in 1 second? So I can calculate this in case of a simple computer as number of cores times cycles per second and flops per cycle. So let me tell you what are these. So this is number of core is very simple. So let's take an example. So they say I have 4 cores in my computer. So nowadays, any even smaller, uh, even a very basic laptop computer will have at least 4 cores, and the advanced one can have even 32 cores, 64 cores nowadays. Cycles per second. So what is this? So it is related to the clock speed of the computer. You know that when you buy a computer, say I have bought a 2.4 megahertz processor. So what does it mean? It means that at the heart of the CPU, you know, it's a digital computer. So we are doing digital electronics. So there is a clock at the heart of the CPU, and that clock runs at say if you have a 2 gigahertz machine, it runs at uh, 2 into 10 to the 6 times per second. Gigahertz is 10 to the 9, right? So 2 into 10 to the 9 times per second. But all that may not be the number of cycles that you can do. Cycles means that cycle of operations you can do per second. A cycle of operations, as you think, as you see that the name is called cycles, you can think of repeated operations. To do a certain amount of operation, computer may need to do a lot more things than just running the clock. So sometimes or most of the times it will require more than so if I have a machine which is 2 gigahertz, I am just now cooking up the numbers, it may require the cycle per seconds will be much lesser. So I just consider it as 2 gigahertz divided by 8. So 1 by 4 gigahertz is the number of cycles it can do in 1 second. And then if I come to very modern Intel processors, for example, Intel Skylake processor. So this is a set of processors which will which was there a few years ago. Even I think that generation 9 probably or 10. Right now we are running at generation 11 of the Core I core processors in Intel. So this can do 16 floating point operations, 16 F64 floating point operations. F64 means that you have 64-bit floating points. So if I go to F32, it will be able to do 32 of. Obviously, the number of bits reduces, so you can do 32 of this.
So what's Skylake?
Skylake is it's I think Intel generation 9 or generation 10 processors used to be called Skylake. See, you
Okay.
have this core i3, i5, i9, right? And then if you want to buy something, you will see that so there are generations of these. So right now we are in the 11th generation. So one of the little older generation used to be called Skylake. I just got these numbers for Skylake, so that's why. Okay, it's a name for a particular generation. The difference between different generation is the way the transistors are implemented. What is the size of the gates, etc., etc. So those we don't need to go to the computer architecture here. Okay, so the question is that, so quickly tell me how many what gigaflop this computer will have. This is a very basic computer. This can be one of your laptops working with these numbers. So what is the gigaflop it will have? 16, right? Because 4 into 2 is 8, cancels this 8, so I have 16 gigaflops. So I have a 16 gigaflop machine. So which means that this can do 16 into 1024 cube operations. I just write 1024 because so when you say gigahertz, obviously it can be 1000 gigahertz also, but I'm just writing 1024 here. Uh, doesn't matter. So these many operations per seconds. Okay. Now let's see, because we arrived from just the Fourier transforms. Let's say I have a DFT, I have a 3D DFT. Okay, three-dimensional discrete Fourier transform. Now, a DFT, if you remember, that it transfers n numbers to the n numbers, and then you have to do multiplication, exponentiation, etc. in each of these operations. So I have that, like we were discussing about, I had an, and the Fourier transform of that was called a capital A small l, and al we had n numbers, an we had n numbers. So if you want to calculate n als from n an, you have to do n square operations. So that's in 1D. So if I have a 3D DFT of size, so I have a three-dimensional box which is size n in each side. So I have n cube numbers. And so here I have n cube numbers, and to get those n cube numbers, I need each of those numbers I need to do n cube operations. So this will require n to the power 6 operations. Okay. Now, if I take n to be say 512, and you calculate that how much time it will take to do this 3D DFT with a machine which has 16 gigaflops. The time will come out to be, guess how much it will be? Can you give a guess?
Sir,
So
one,
not doing very big things. So we have a 512 cube data, and that from that we are calculating the Fourier transform of that data. Okay. So how much time do you think it may take?
sir, 1/16th of a second.
1/16th of a second. So why you said 1/16th of a second?
Sir, because 16 times 1024 cube operations can be done in a second. And
Right. But how many operations do you need to do?
sir, 512 ki power 6.
So that is only 16. 1 by 16.
Yes, sir.
How? 512 to the power 6 is 10 to the 24 to the power 6 by 2 to the power 6, right?
Oh, yes, sir. Yes, sir.
If you calculate, this will not take in seconds. This will take in tens of years. Okay, 12 years. Well, of course. So, see, if this is a program that you have to do in your PhD, you cannot do it. PhD is only 5 years. Of course, you can refer to better algorithms. Like if you look at the video that I have uploaded uh, for the
So
lab.
how n is equal like
Yeah,
n
go ahead.
approx to 512?
How?
Uh, how did you take n
No, I
512?
didn't take. I have just taking an example. So I'm said that n as around 500, 512 is the number that I'm using. You can ask the question. So that is the size of the Fourier transform, right? So that's
Okay.
I've taken 512, which is not very unreasonable. People have done a lot better than that nowadays.
Yes, sir.
Okay. So, like for example, in cosmology, there are certain simulations where you have to do. People does now 4096 size FFTs in one time step, and then you will do like 10 to the 6 time steps. Okay, so you can imagine that how much amount of operations is required for that. Obviously, those are done in big machines, and then so that's the other point that I was trying to say. So if you use the algorithm FFT, so instead of here it requires n to the 6 operations, the same GFT can be calculated with a different algorithm called FFT. I have not discussed it, but I have showed you in that video that how it speeds things up. So this can be calculated in n to the 6 log 10 n to the 6, these many steps, and then the time comes out to be much lesser, 0.03 seconds only, and you can see that that is considerable amount of speed up, 12 years to 0.03 second. So sometimes the algorithm can come to your rescue. You can do a task much faster. This is happening just because I have a log 10 of n to the 6 here, and log of very large number is much lesser than that particular number. Okay, so we'll proceed, but if you have any question at this stage, we will take that first. All right, so what you see here is that even to do very simple operations in computer, because we are doing the same operations repetitively many times, it may take quite a large amount of time to do that computation. Sometimes there are better algorithms which are at your disposal, and you can speed up the computation just changing the algorithm. Sometimes you cannot. So another example that I will give you where you can speed up is that, just let me keep it here. And yeah. So if I want to calculate e to the power x, so what is it? Is 1 plus x plus, this was one of your exercise, etc., right? So the way you can calculate it is that in each term in the series, you can calculate, like the first one is 1, and then the second one is of course x. Then when you calculate the third one, you multiply x 2 times and then multiply 1 into 2 and then divide. When you calculate the fourth term, you multiply x 3 times and then multiply 1 into 2 into 3 and then divide. So that's one way of doing it. But you see that when you go to larger and larger terms, it takes a lot more time. The other way of doing it is that when I am calculating x cube by 3 factorial, x square by 2 factorial is already calculated. So I can just multiply that by x by 3 and then add up. So that will be much faster, because in each step you are doing only one division and one multiplication. Okay. So this is speed up in algorithm, but always it is not possible, obviously. I mean, there will be cases where we will see that this type of speed up is not possible. So then the only way you can get it out is that run things in parallel. Okay. A classic example of a parallel computation is that think of that you have gone to a store where you have only one cashier. Okay. And the cashier is processing the queries from the customers. So the customer is taking 3 items, and then the cashier processes 3 items, tells you, adds up the value, and then takes the money from you and give you the 3 items. Then the next person comes and carries on like this, right? But the problem here is that obviously then there will be a large queue if there are a lot of customers. And the example of our parallel computing is also obvious, that you, instead of one cashier, you have 5 of them or 4 of them, and then different people goes to different of these. So it will be like, you can expect that there will be considerable speed up, and then there will be no queue which is gathering because of this. Okay, so let's move on. So we need to understand that. So once we realize that we have a requirement for parallel computation, we need to understand that how to do parallel computation. So, and for that we need to understand how a basic computer works. Okay, so let's see how a basic computer works. And can you imagine when this was coined? How a basic computer, the computer which is used in today, I mean, we are using right now, the basic architecture of its working was given as early as in 1945, and nothing much changed on top of that. It's only improved.
So with Turing or Babbage,
Neither of them.
uh, then who gave?
So this is by John von Neumann. So he laid out a way of doing computation with what we call programs today. So previously, if you want to do a computation, the program is hardwired, means that one computer can do only one type of computation. So you cannot make the computer do any other type of computation. Then what you need to change is literally change the connections in the computer. Okay. So Newman's idea is the following. So this is, let me draw kind of. So you have the main processing unit, which is usually called an arithmetic logic unit. Okay, so let me draw this below. So what is an arithmetic logic unit? So this does all the operations. Okay. So let me just list a few operations which it can do. So this does all the basic operations, which is the actual computations are all done by this part of the computer. So this can do addition without carry, addition with carry, subtractions, different types of subtractions, two's complement arithmetic. It can do, for example, it can increment or decrement. Okay, so it can so in the memory it can go to the next memory or it can go to the previous memory. So that's increment and decrement. It can do many other things which I am not listing here, and then it can do logical operations. Logical operations are like and, or, etc. And many things. So all the things, all the basic blocks of computer that you learn in your digital computing, digital electronics, so those are all done by this ALU. And this is the thing which actually does the computation. Okay. And then what you have is a set of what you call the program or instruction. So this is essentially what you want to do. You write in your own language, and then there is a compiler which is translating into the language of the machines, but it is all that you want to do. And then you want to do this operation on some numbers, which I call data. Okay, both of these stays in the place we call memory. So these are the things which are states in the memory. Okay, and then from memory it goes to a control center. So this is the place where your instructions are read and understood by the logic, and then it is passed to the ALU. ALU does the operation, and these are double-headed arrows, so returns it back to the control unit, and then it can be returned to the memory. And then you can have, obviously, you need to say that start the program, etc. So those things are there. Okay. So if I give you an example, say I have this set of instructions that so load A, load, let's write this as capital. Okay, store or save C. See, basically what there are four set of operations here. So one is load A from the memory, load B from the memory. So from memory, the two data. So these are data. This is also data. So these three data are getting load from the memory to the control unit, and then you have the instructions. So all these four are instructions. The actual arithmetic operations which is being done is this. C is A plus B. So these four instructions and two data, A, B, and three data, A, B, and C. These are all load into the memory. Load into the control unit from the memory. Goes to the ALU, does this operation, returns you back C, and the C is being written to the memory. So this is how a computer works. Okay, and it is important to understand this, because then the reason it is important to understand is that you know that if I just have C equals to A plus B, if I don't have a number stored in A and B, but I just do C equals to A plus B, the computer will give you an error because it's not getting any data, but it's getting an instruction to operate on a data. Okay, any question? All right, let's move on. Now the question is that, so this is one unit of operation, right? There is no parallel computation involved here. This is a basic way a computer has to operate, so which was given by von Neumann in 1945. The advantage of this thing is that this instruction is something which you can give as an input, and then it will store in the memory. So that's the program that you have loaded into the computer. And now you can keep on, so you can give an execute command and the computer will run the program on the data. It can generate the data or crunch the data instead. Data crunching means doing this operation C equals to A plus B. Okay, I mean many other operations, but that's one of the operations. Now the question is that how can you arrange these basic things to do a real computation? Okay, so there are different ways of handling a computations. If we go back one step, one slide, we have seen that we had two major players here. One is the instruction, the other is the data, right? So this way of looking at the computation depends on the instruction and the data. So I write instruction here and I write data here. So what I can do is I can have a single instruction and a single data in one clock cycle. Okay, so I will explain what I mean. So this is often called single instruction, single data. So you know that people like acronyms. So this is one of such acronyms. So what happens here? So we have so let us go back one step. This entire thing, which is the control unit and the ALU, are often termed as processing unit, because this is done all the processing. This is one processor. Okay. So I will just call it a processing unit, or you can call it central processing unit as well. So but let's call it a processing unit only. So I have a processing unit. This processing unit is fed with one set of data and one instruction in every clock cycle. So this goes into it in every clock cycle. So let's say that let's look at the previous example. So I had load A, load B, C equals to A plus B, and then save C, right? So how many clock cycles will require for this program to run? So 1, 2, 3, 4. I have 4 instructions. It will require 4 clock cycles. Okay. So if my computer is capable of running 4 floating point operations a second, this will take 1 second. So there is no parallelism here. So this is a serial programming. The instructions are going one by other to the processing unit. But then that's not good. I mean, that will be slow. So then you come to single instruction, but multiple data. So single instruction, multiple data. So what do I mean? So I mean that, so I have the instruction common, but I have different datas. Now what I can do is I can use two processing units. Each will get the same instruction, but it will operate on different datas. Okay, you immediately see that this is obviously running in parallel. So in one clock cycle, I can do two identical tasks. So for example, I can, if I just carry on with the previous case, so I have load A, sorry. So this can be one operation, sorry, this can be one processing unit doing, and the other processing unit is doing on the other set of data, which I call A2, B2, C2, and so on. And you get the idea. So this is done by one processing unit, and this is done by the other processing unit. You see that each processing unit is doing the exact set of instructions, following the exact set of instructions, but with two different data sets, A1, V1, C1 and A2, B2, C2. Now you can have multiple instruction and single data. So I am not doing the block diagram anymore because you understand what will happen. So there will be more than one instruction operating on the same data. And this is also parallel, obviously. And one example will be, for example, so if I just carry on with the same thing, so load A1, load A2, then I calculate C or load A and B only. C is A plus B, D is A minus B, and then save C and D. Okay. So if these are my set of instructions. When you come here, you realize that these are two instructions which can be done together at the same time, which can be calculated at the same time. So now what I will do is this will run in single instruction, single data mode. This will run in single instruction, single data mode. But this part will run in multiple instructions. Two instructions are here. So one is addition, one is subtractions. But the operation is happening in the same data, which is A and B. So this will run in multiple instruction, single data mode, and then you will go back to the serial mode again. So part of the program can be multiple instruction, single data. And then you can have multiple instruction, multiple data, and I will not give you an example for the time being. You can think of an example for this. Okay. So let me pause here, and if you have any question, please ask now.
So multiple input, multiple data can be like in the
Multiple
shop,
instruction.
multiple instruction, multiple data. Like one is cashier, one is say packing the bags, one is maybe. So there are different jobs to be done, and various people are being queued in various lines.
Right, right, exactly. So there
Okay.
are, I mean, okay. So let me tell you at this point that the parallel computation itself is a huge industry. It's obvious, and I mean, there are humongously different ways different parallel ways one can separate out different types of parallel computing. We will only discuss a few things, and we will only explore in practice one particular type of parallel computing, which is called shared memory processing. Obviously, in two lectures and in one lecture and one instruction type of lecture, implementation type of lecture, you cannot do more than that. But these are the basic ideas which will, so if you do parallel computing at some point, if you are in computation, you will need to do, and then you will see that if you do not understand the basic, you will actually slow down a process doing parallel computing than speeding it up. Any question? All right, let us proceed. Let's ask the question that, okay, so I can do it in many different ways. And we have also understood by this time that, so for example, this program, the single instruction, single data mode, if it is running, if I have to just add A and B to C, there is absolutely no way I can make a parallel version of this program, because I cannot load A and B to two different processing units, because they need to be added up later. So they has to be loaded into the same processing unit. And then only that processing unit can do the addition. And then that is what can only save C, the value of C, back to the memory, which means that this has to be done in a single processing unit. There is no way you can break it up. Single instruction, multiple data, you see that here the exact same instruction can be carried out in different processing units, which means here this can be the operation where two arrays are being added up, right? So one array is so one array is A, the other array is B, and then I have A1, A2, A3, A4, which are the elements of the array. You can think of adding two vectors only. So you are adding up two vectors, A1, A2, A3, A4, B1, B2, B3, B4. So if I have four processing units, I can just run them parallelly. And here the entire program is running parallelly. The full program is being parallel, which this type of program is obviously very rare, but one can design programs such a way that the full thing is parallel with some cost. When I come to multiple instruction single data, you realize that here, at least in this example, only a part of the program is parallel. The rest of it is running serially. This will be the case for most of the programs, because you see that if I have to do some work, I have to load A and B. Even if I go to single instruction multiple data, the part we have not written here is that this loading A1, A and B, so which I kept in the same block. But if you go into practice, you have to load it from the same memory, and that will happen. So it depends on how the memory is distributed, so that we'll discuss. Depending on that, it may happen that this loading part is happening in serial mode. Okay, so part of the program will be serial, part of the program will be parallel. Okay, so with such a program, the question is that what is the benefit of doing parallel computing? And this is this is something which is very important to understand. We'll see why. Okay, so the question we are asking is time to do. So say there is a process which is time to do in serial mode. So single instruction, single data mode is TS. So this is the amount of time the process takes to be done in the serial mode. Okay. Now, as we said, that the fraction of the program can be parallelized, and the fraction has to be done in serial mode. So the serial fraction of the program is, say, fraction serial, and the parallel fraction of the program is fraction parallel. Okay. And say I have number of CPUs. So let me write CPUs, central processing unit. The central processing unit is a little bit different from a processing unit. We'll go to that shortly. But so number of CPUs is, say, NC. C for CPU, or let's say NP, number of processors.
So,
Yeah,
what do you mean by fraction, like serial fraction and parallel fraction?
right. See, here in this case, multiple instruction single data mode, I had one, two, three, four, actually six, so save C and save D. So there are six instructions, right? Only two of them can be parallelized. So which means one third of the program can be parallelized. So each of these are one floating point operations if you think of. So one third of those floating point operations can be parallelized, two third cannot be parallelized,
Yes, I
right?
got it.
So serial fraction is two third and parallel fraction is one third.
Yes, sir.
And then you have number of CPUs NP. Okay. So now how much time it will take to run in parallel mode? Time to run in parallel. So if I call this TP, so TP will be, so the parallel fraction FP can now run in NP CPUs. So that takes only FP by NP time. And the serial fraction takes the exact same time as it used to take. So this is the time to run in serial. Time to run in parallel. You see, Fs is the serial fraction. So if the total time is Ts, to Ts times Fs is the time to run in serial mode. So that is what you get here. And the parallel mode, the parallel fraction can be parallelized. So if I have NP CPUs, so each CPU does its job. So it can be Fp times Ts by NP. So it's the first one. So we can say that, so how much is the speed up in doing this? So that's essentially the ratio of single to the parallel. So obviously Ts is greater than Tp. So this is 1 by Fp by Np plus Fs. Okay, any question? You see, this expression, this relation that we come about is very simple one, obviously, but it tells us a lot of things. Let's say that I have a program where half is parallelized, half can be parallelized, and half cannot be parallelized. So both of these fractions are 0.5. Okay. So then what is the value of CS? CS is 1 by, so 0.5 is in the both cases. So I can just write 2 by 1 plus 1 by NP. Is this fine? So both FP and FS are 0.5. So I have 1 by 0.5, which is 2, and then 1 by NP plus 1. So I give you a computer which is the fastest supercomputer possible at the present day. What is the maximum gain you can have? What is the computation speed up you can have? Say NP is 10 to the power 20. So I give you 10 to the 20 processors. What is what is the value of CS max? Come on,
2.
it's 2. So you cannot, whatever you do, you cannot go past 2. So this program will not, I mean, it's not economic to run in a very large number of processors because we will not gain much speed up. You can try to plot this and see what. Try to plot CS as a function of NP and we'll see what happens. And so let's say that the fractional part which can be parallelized is 90%, and the part which cannot be parallelized, the serial part, is 0.1%. So CS will be 10 by 9 by NP plus 1. So what is the maximum value now?
So what is NP for supercomputer?
Which supercomputer?
Like in general, NP takes what values for like
Ah,
supercomputer?
good question. So I'll ask you this as an exercise. So there is a supercomputer in our campus called Param Shivaya. Okay. So the link to the supercomputer is there in our website. So all of you please go and check that what is the value of NP, how many processors it has. Okay.
Okay, sir.
Okay. So just check by yourself what can be the maximum number. So this will be maximum 10, right? So this is something that you should calculate when you are trying to parallelize the program. So say I give you 1000 processors and you write a program running this 1000 processors. It takes say 2 seconds of time, and somebody else may be running it in 10 processors. It will take 2.1 second of time. So you are then wasting a lot of processes, right? So here, for example, if just imagine if NP to be 1000 and NP to be 10. If NP is 10, then it is 1 plus, sorry, say NP is 100. So it is 1 plus 0.09. 10 by 1 plus 1.09 is almost 10. And if it is 100, I mean, you don't get much, right? Just multiplying the processor by 10 times. So that one has to understand that before you start designing your code. So you try to design your code such a way that you have more part of it can be run in parallel mode. If you cannot if you cannot design your code in that way, there can be problems like that. So then obviously there is no reason that you will try to use a parallel computer. Any question?
So,
Yeah.
uh, like supercomputers and all, their the names are given based on the number of processors, right?
Not always. The Param Shivaya name doesn't have any number of processor in it.
No, like they are called supercomputers because of huge
Yeah,
number
yeah,
of.
yeah. Okay, obviously, yes. Yes,
Okay,
because they have a lot of memory and then they have a lot of processors. So,
okay,
see, finally, there are two numbers which matters. I mean, obviously, if you go to deeper level and what type of program can be faster and what type of program not, so then many things matter. But two numbers grossly matters. One is what teraflop is your computer and how much memory uh, per processing unit you have. Okay. So these two numbers you have to be aware of. Okay. So let's ask the question. Sorry. Let's ask the question that what are the different ways a computation can be parallelized? See, we saw that in terms of data and instructions, how it can be parallelized, but in terms of processes, how it can be parallelized. Okay. But these different classifications, it's not that they're completely separate out. So you'll see that one part of this matches with one part of the other types of classifications. But again, these are very basic things which one need to understand to uh, do the parallel computations more effectively. Okay. The first thing is called bit level parallelizations. Okay. And I will not go through this in detail. I will just tell you with examples. A bit level parallelization will be the following. Say I have 128-bit registers. So what is a register? It's so one 128-bit register at once can store 128 bits. Okay. So these 128 bits has to be operated on first. The ALU will do operations on these 128 bits, and then it will pass it back to the process, the scheduling thing, which is before the ALU, and it will get the next 128 bit, which will come. Okay, so this 128 bit can contain both instruction and data. Now, when I say bit level parallelization, so one example will be, say I have 32-bit floating point numbers, and in 128 bits, I can store 432 bits floating point numbers. Okay, so now, like in the previous case, we are doing this operation C equals to A plus B. But what I can do now is that I can load 4 A's together and 4 B's together, do 432 bits operations together, and get 4 C. So in one clock cycle, I am actually doing 4 operations instead of 1. Okay, so these are sometimes also called vector parallelizations, because you are like, instead of adding two numbers, two scalar numbers, you are adding two vectors. You are adding a1 b1, a1 a2 a3 b4, a4 with b1 b2 b3 b4 at the same clock cycle. Most modern day computers, by implementation, they have the vector capabilities. The next thing is called the instruction level. So what is an instruction level parallelism? So when I talked about the ALU, it does not, so we said that it has many, it can do many operations. So ALU can do many operations, many different operations. So it doesn't have only a single adder which will add two numbers. It will have many such adders inside it, right? So which means, so that's why when you talk about, today we talk about integration density. So that's very important, because if I can make my transistor smaller, I can pack a lot more, say, adders inside my processor. So it can do a lot more operations at the same time. So in our previous example, what one can do is that, say, for example, this, so each of these numbers, C, A, and B, is still 128 bit only. So we are using 128 bit floating point numbers. But now what I can do is, because my ALU has these different adders, so I can say I have in my instruction, I have C equals to A plus B, D equals to A minus B, E equals to A into B, etc. These can go to different parts of the ALU and done together. So this is called the instruction level parallelism. Usually nowadays, most of the operating system knows how to do instruction level parallelism. You don't need to do it by hand. It will process the data, understand that these bits can be done together in the ALU, and then it will send all of them together and get it done. Then you have task parallelism. So what it can be the task parallelism? The task parallelism is different now. The task parallelism is that, so these different tasks C, D, and E. So I call this now this C, D, and E, these three calculations which is done over there. These can go to different processing units now. Okay. This particular case, as you see, that this can be just done by the instruction level parallelism, but I'm just giving you an example. So if I do it with the task level parallelism, what I will do is that I will send these different tasks to different processors. And so we are running out of time. So I will start discussing these in the next class again. But you see that once you are trying to do this, there is now a question of synchronization, which we will discuss again next time. Why this comes about? It comes about because, see, after doing c equals to a plus b, d equals to a minus b, etc., you have another step which is writing back c, d, and e into the memory, and then you can load the next stage of set of data. But here, what will happen is that addition and subtraction will probably run at the same time, but multiplication will require more time. So you have to wait for the multiplication to finish before you can load the next state of data. Okay, so I'll stop here. And there is one more way of doing the parallelism in different methods, but we'll go through this again in the beginning of the next class. So if you have any question at this point, please raise.